Is everything we think we know about the universe wrong? Is our understanding of dark energy fundamentally flawed? Very possibly. Let's dive into some recent findings from DESI, or the Dark Energy Spectroscopic Instrument, to talk about these weird findings, what dark energy is, and how all of this might change our understanding of the universe. Okay, so let's start with what is dark energy. It's not really related to dark matter, even though they have similar names. They're both called dark because they're not directly observable. We infer their existence based on how we've observed our universe behaves. Basically, scientists think dark energy exists because, as far as we can tell, the universe is expanding at an accelerating rate. 10 billion years after the universe began with the Big Bang, the expansion of our universe started to speed up when dark energy began to dominate our universe. Breaking that down, it's not just that the universe is expanding, it's that the rate of expansion is increasing. Gravity tells us that this shouldn't be happening. It's as if you threw something in the air here on Earth and it kept going up, which we know shouldn't happen. Some sort of energy has to be driving that acceleration, and scientists have given it the name dark energy. We think it comprises about 68.3 to 70% of the universe. Then, what are the prevailing theories about what dark energy might be? There are four main ones. First, it could be vacuum energy. This is the idea that there's a theoretical energy distributed throughout space. What if there were pairs of particles and antiparticles and they canceled each other out? The energy created by them coming into existence and then being canceled out could be the force behind dark energy. But this type of energy creates too much energy to the point where stars and planets would never have formed. Second, some scientists think that dark energy is just wrinkles in space, a defect in the fabric of space that formed in the early universe. Third, it could be some sort of fluid or energy field that behaves opposite to normal matter. And finally, some think dark energy is a defect in Einstein's theory of general relativity, and that relativity and gravity work in a different way when you're talking about the scale of the universe. Basically, this says that dark energy doesn't exist, and you can modify our understanding of gravity in a way to account for the accelerating expansion of the universe. Right now, the Standard Model of Cosmology is how we understand the universe as it exists. It says that the Big Bang created the universe, and the universe is about 5% regular matter, 27% dark matter, and 68% dark energy. It's also called lambda CDM, or the lambda cold dark matter model. Lambda, which represents dark energy, is constant over time in the Standard Model. That's key. We have no confirmation that dark energy exists. The thing to understand about the Standard Model is that it is the best explanation scientists have found for our universe. People think that because there are parts of the Standard Model we don't understand, like dark energy and dark matter, that it's some sort of cop-out. It's not. And more, we have been discovering things that have challenged the Standard Model. That means we may fundamentally misunderstand our universe, and it's time to go back to the drawing board. So now, what's wrong with what we think we know about dark energy? Let's talk about DESI. This is an instrument installed in 2018 on a telescope at Kitt Peak Observatory in Arizona. DESI has a 5-year observing lifetime, during which it will measure and analyze the light of 30 million galaxies and quasars. The goal is to accurately measure the expansion history of the universe. Well, we just got DESI's first-year results, and they basically might fundamentally alter what we know about the universe. This new data tells us that dark energy may not be constant. It may be weakening. DESI created the largest 3D map of the universe ever that stretches back over 11 billion years. The way DESI works is to collect light from galaxies and quasars, which are extremely luminous, active galactic nuclei that emit radiation across the electromagnetic spectrum. But to create an accurate map of the universe, you need to know how far apart things in it are, which is why DESI worked to make redshift measurements that are as accurate as possible. As the universe expands, everything within it stretches, including light. The wavelength shifts towards the longer or redder end of the spectrum, hence the name redshift. That's the reason that high redshift galaxies are also the ones that are further away from us. Scientists can use redshift to measure how the universe is expanding, at what speed it's expanding, and to figure out the distance to the oldest objects in the universe, as well as the age of the universe. DESI is measuring light, but also getting measurements on the expansion of the universe that are as accurate as possible by looking at BAO, or baryonic acoustic oscillations. In the early universe, after the Big Bang, the universe was a thick, hot soup made up of light and matter. Scientists think matter was evenly distributed, but gravity was trying to pull clumps together to form the first stars and galaxies. But as the galaxies formed, the matter heated up, and then that heat counteracted gravity and pushed objects apart. And then it cooled off, and gravity pulled it back together. This cycle created baryonic acoustic oscillations, basically sound waves that spread outward in bubble-like formations. About 380,000 years after the Big Bang, atoms formed, which cooled down matter enough for gravity to overcome that heat. As larger structures like the earliest galaxies began to form, these oscillations were imprinted and frozen in time. We can still read those frozen bubbles today, and because they're all the same size, scientists can tell how far or close to us the galaxies they're imprinted upon are. The way these BAO signatures have changed over time is one way we can measure the expansion of the universe. And now DESI tells us that dark energy may not actually be constant over time. It appears to be weakening. We may, in fact, live in a variable universe. Okay, so now for the caveats. DESI data alone is not enough evidence to disrupt the Standard Model of Cosmology. Remember, models are not sacred, and some scientists may be too attached to them, but most just want to describe the universe around us as accurately as possible. Lambda CDM still does that. The things here that differ from Lambda CDM are pretty small. It could be just measurement error. DESI has 4 more years to collect data, so we will keep an eye on this for sure. But what makes this compelling, and the reason I'm spending this time making an entire video about it, is that when you add the DESI data to other data we have collected, specifically Planck's measurement of the cosmic microwave background and recent supernova maps, things get very interesting. The fact is, this is not the first time we have gotten an indication that dark energy might be variable. A recent survey of 1,635 Type 1a supernova, which have standard brightnesses and therefore can be used to accurately measure distance, found that observed brightness didn't line up with the idea of a constant lambda. This is just one of 3 recent supernova studies that found the same thing. And then there's the issue of the Hubble constant. I went in depth on this a couple of months ago. JWST confirmed that the Hubble Space Telescope's measurements of the Hubble constant are accurate. That might not sound like a big deal. Watch my video for the full analysis, but basically the Hubble constant measures the rate of the expansion of the universe. Measurement of cosmic microwave background, which is light left over from the Big Bang, gives us one value. The Hubble Space Telescope surveys give us another value. There cannot be 2 values of Hubble's constant. I said at the end of that video that if both values were true and Hubble's constant changed over time, which would mean that dark energy was variable and not constant, it would break the Standard Model of Cosmology. The model isn't broken yet. There's still a lot about it that accurately describes our universe as we have observed it. But the fact that 3 separate sources of data, DESI, supernova surveys, and the cosmic microwave background are all pushing us to consider the fact that dark energy might not be constant. That's pretty compelling to me. You can bet I will be doing more on this as we get more data, but for now that's all I have to tell you about dark energy and possibly throwing the Standard Model out the window. Thanks for watching. I am Swapna Krishna, and this is Ad Astra.